Okay, so today we're going to venture into interpreting position versus time graphs as well as velocity versus time graphs. Okay, there are going to be a set of rules that we are going to learn as to how to interpret each, but it is worth noting that the rules to interpret a position versus time graph are going to be different than that for a velocity versus time graph. So when we get to the point we transition to velocity versus time, know that the rules we're going to use are going to change. How are we going to describe them? We're going to describe them in terms of the object's displacement, speed, and acceleration, a lot like we did in our lab. So our goal by the end of it is to be able to determine what's happening in terms of the displacement, speed, acceleration for both types of graphs. Okay, so let's start with position versus time graphs. We'll start with the displacement, which I think is one of the easier things to do. To determine the displacement on a position versus time graph, we simply have to look at the slope. Any positive slope tells us the object is going to move in the positive x direction. So let's just give some sample data here. Let's say we see this on a position versus time graph. Okay, position is along our y-axis, time is along our x. We do not necessarily need to label it, but here's a tool that I use to kind of help you figure this out. You will notice that these graphs do not have a scale drawn in. Sometimes I kind of put in my mind a make-believe scale, something that would be helpful to determine what's going on. And if we use nice round numbers, like we start at 0 at the origin, and let's say we go to a positive 10 and a positive 10 along each axis, kind of helps us to figure out what's going on. So with the graph that's shown here, with the straight line, it looks like we're starting at about a position of, I don't know, maybe 2 or so, and finishing at a position of 10. Since we're in the first quadrant, okay, that's what we get. And if an object or a person starts at a position of 2 meters, let's just say, and finishes at 10, they have to be going to the right. Now, we are not limited to straight lines. Another possibility for this that would be a positive slope might be that curve. Okay? We still will end up going to the right for any positive slope. This might be a little odd example, but I kind of use it as my way of framing it. There are 3 possible positive slopes we can have on a position versus time graph. If you kind of draw all 3 of them together, we have the straight line, we have that curve, and we have that curve. I don't know, to me it kind of looks like it could be a coffee bean, okay, but those 3 lines, okay, the 2 curves and the straight line, those are all the possible combinations for a positive slope. So if we're going to see any of that on a position versus time graph, that's going to tell us that our object has to be moving to the right, because we'll be starting at some lower position and finishing at a higher position. A negative slope is going to be anything that's going to have a negative displacement. Okay, so we kind of go the opposite direction. Okay, so we have 3 possible combinations there. So anything that would be a negative slope, okay, or let's just say negative slope. Okay, those are going to be an object that's moving in the negative x direction or moving to the left. Okay, last one, 0 slope, which is anything that would have a 0 slope. And let's pretend for a minute I actually drew a halfway decent 0 slope line. And again, we kind of put our pretend scale up here, even though this is not the actual scale. We're just putting some numbers to it so it helps us to make sense. It looks like that our object is sitting at about 5 or 6 meters or so and staying at 5 or 6 meters. So 0 slope, the displacement is 0, or the object is stationary. So that's position versus time and figuring out displacement. The next thing we need to do is we need to figure out the object's speed. So is the object at a constant speed, or is it going to speed up, or is it going to slow down? Now, an object moving with constant speed is going to have a constant slope. What does that look like? Any constant slope is a straight line on a position versus time graph. So any straight line, we know that the object is moving with a constant speed. For an object that is speeding up, we're going to see an increase in the slope. So one of our possible curves we could see might look like that. Now, if we remember back to a couple classes ago, we can use some skills to kind of dissect this. How do we figure out whether it's an increase in slope? That means that we would have to start, if we were to draw a tangent line right here, okay, we could draw it a lot larger than that, but I don't want to confuse us. At that point, we would be at a slope of, well, pretty close to 0. So that would tell us that our object is relatively stationary there. And then later in the graph, if we were to draw a tangent line at that point, we would see there would be a very steep slope. So the object would be traveling very quickly at that point. So that curve is showing an increase in slope, so that object has to be speeding up. The other possible combination for an object speeding up is going to look like this on a position versus time graph. It also starts with a zero slope at the beginning and a steep slope at the end. Okay? So how do I figure out whether something is speeding up or slowing down? I do ask myself, where is the zero slope? If the zero slope is in the beginning, we know that the object should be speeding up. How do we show the object slowing down? That would be the decrease in slope. So it means that we're going to finish with the zero slope. We're going to finish with the zero slope, or close to it. Okay? So we start with a steep slope, finish, close to a zero slope. So those would be our possible combinations for an object speeding up, okay, in the middle, and then the last set of graphs, okay, for an object that is slowing down. Okay, so now we have displacement, we have speed. Okay, in order to get the last piece, the way that I frame my logic for this, we have to get those two correct. So we need to be able to accurately determine what the displacement is. We need to accurately determine what's going on with the speed. Okay? So if an object is speeding up, the acceleration and displacement vectors are going to be in the same direction. And if the object is slowing down, they're going to be in the opposite direction. So here's how we frame our thinking with this. Okay? The acceleration, we're trying to figure out what's going on with it. So if we have an object that is traveling at a constant speed, I hope we understand that the acceleration would be zero, because for right now we're dealing with motion in one dimension. So if it's traveling in a straight line and it is traveling at a constant speed, it would not have an acceleration. Now, this is what kind of gets some people in terms of trying to understand acceleration. But these rules will also apply to the mathematics that we're going to do a little bit later when we use the kinematic equations, and then checking our work to see if an acceleration is positive or negative. So here's how it works. Okay, let's start with the first part. If an object is speeding up, that means it's getting faster, the acceleration displacement vectors are going to point in the same direction. So if you speed up when going to the right, you would have a positive acceleration. So there'd be a positive displacement because we're going to the right, we're speeding up, it would be a positive acceleration. If you are going to the left, that would mean you would have a negative displacement and you're speeding up, you would have a negative acceleration. And usually what kind of gets people about that is they don't think about what happens when we start going to the left. A lot of people usually have a pretty good idea what happens if we were to frame our motion as in traveling to the right. But if an object is traveling to the left and speeding up, the acceleration must have the same sign as the displacement. Now, if an object is slowing down, those two vectors are going to point in opposite directions. So if you are slowing down, going to the right, you would have a negative acceleration. The one that really gets people is going to the left and slowing down. You can kind of think of it as a double negative example, okay, in the fact that you go to the left and slow down, it ends up being a positive acceleration. So, how do I do it? Okay, well, just following that rule. But if we're looking at an object that's speeding up, okay, once you determine, if you determine, let's just say the displacement is positive for an increase in speed, well, then the acceleration also has to be positive. Okay, separate from that, for the same increase in speed, if the displacement is negative, the acceleration has to be negative. Okay, if we have a decrease in our speed, then we know that they have to point in opposite directions. So you would have to determine, well, if the displacement is positive to start off with, then we know the acceleration would be negative. Or, separate from that, if the displacement were negative, then the acceleration would be positive. And again, I know this might be confusing, but it's really important to understand the relationship between whether we have an increase in speed or decrease in speed, which is why in the lab that's what we asked you to focus on. It really helps to frame what's going on with it. There is another way to think about acceleration, and when we do it with mathematics, it's easier to do. It's based off velocity. Okay? And when we do velocity versus time graphs, we'll actually see it might be a little bit easier for us to kind of frame. But for right now, we're going to do it based off of speed. Okay? So that is a position versus time graph interpretation. So let's go ahead, let's do a couple of quick examples here together. Okay? So our first sample, position versus time. Okay? Well, we see we have a positive slope. Remember that slope determines the displacement on a position versus time graph. So we would have a positive displacement. A straight line tells us that our speed has to be constant. Now, we're not necessarily asked to do it here, but we will be in some later examples. We are going to have to be able to differentiate between whether that constant speed is fast or slow. Remember, the steeper the slope, the faster it's going to be. So relatively speaking, I think most of us could agree that that's a very gradual slope, so that's going to be a relatively slow speed. And we have a constant speed, so the acceleration has to be 0. Okay, next graph. Okay, we have a curve here, but we still have a positive slope. Remember, it's kind of like our positively sloped coffee bean, so therefore we have a positive displacement. For speed, think, what is the slope at the beginning? What is the slope at the end? Where is the 0 slope? The 0 slope is at the beginning, so that's when we're at rest or we're not moving. So this has to be an increase in speed. And since it is an increase in speed, that means that our acceleration has to be the same sign as to what our displacement is, which in this case would be positive. Okay, fourth quadrant. We haven't shown you a fourth quadrant graph yet. Fourth quadrant doesn't mean anything other than the fact that all of the motion occurs to the left of the origin. The exact same rules apply. For both of these graphs, it's a negative displacement. For both of these graphs, it is still a constant speed. How do we know it is constant? We have a straight line, a constant slope. And if we assume that these two graphs have the exact same scale, our last graph is going to be slow, while our top graph is going to be fast. Why? Steeper slope in the first of these two. Okay? More gradual slope in the second of them. And since it's all constant speed, the acceleration is going to be 0. Now, before we transition to velocity versus time graphs, I want to re-emphasize that the rules we use for these are going to change. So when we start talking about velocity versus time graphs, we need to make sure that we're not using the rules for position versus time graphs, because what we're graphing changes. So on a velocity versus time graph, we're actually even going to change the order at which I'm asking you to look at things. Okay? We still will start with displacement, but what comes next is the acceleration, and then we'll come back to what's happening with the speed. Okay, so when we interpret a velocity versus time graph, we're going to follow these steps. Determine the direction of the displacement. Positive velocity values indicates the object is moving in the positive x direction. Well, how do we read that? How do we get positive velocity values? That's going to be anything in the first quadrant. Negative velocity values indicate the object is moving in the negative x direction. That is going to be a fourth quadrant graph. Remember, we're not going to have a second or third quadrant graph because that would mean that we would have negative time values, which just isn't going to happen. So that should be easy if we remember that on a velocity versus time graph, we simply look at the quadrant. First quadrant, positive displacement. Fourth quadrant, negative displacement. No matter what is shown in those quadrants, That's what we get for our displacement. Before we move on, let's just talk very quickly as to why that's the case. If you think about a first quadrant on a velocity versus time graph, let me draw a quick one here on the board that has both the first and fourth quadrant in this, so a velocity versus time graph. Any data that would be graphed, let's choose a little different color, any data that would be graphed here in the first quadrant, no matter if it's any of these lines here, which you're actually going to see this graph in a minute and a second, no matter what's there, the first quadrant, we're all having positive velocity values. And if we were to put our scale, our imaginary scale of 0 to 10 to negative 10, then our velocities are all positive. And if you have a velocity of, let's just say, positive 6 meters per second, or positive 2 meters per second, or positive 10 meters per second, they're all positive, which tells us we have to go to the right. Anything in the fourth quadrant, the same way. Okay? There's 0 to negative 10, so negative 5, negative 4, negative 9 meters per second. They're all negative, which tells us we have to be going to the left. Number 2, to determine the object's acceleration, this should actually be the easiest part because your slope is your acceleration. Positive slope, positive acceleration. Negative slope, negative acceleration. 0 slope, this is the constant speed, or 0 acceleration. Now, here's what's different about a velocity versus time graph. Here in our physics course that we're offering, we're only going to be showing straight lines on these velocity versus time graphs. Okay? It is possible to have curves, but what that would mean is that there would be a change in the rate of acceleration, and we're just not going to go that route in the context of this class. It is possible, but all of our velocity versus time graphs we're going to see are going to have straight lines. Okay. Now, before we get to some other samples, I actually want to take a moment and expand on the kind of graph that we've drawn in here. Let's do this. Okay, let's make a new graph. Okay, so I want to show both the first and fourth quadrant graphs. Okay, so this is velocity versus time. And let's say that we kind of have these different graphs, these data points, shown differently on these graphs. So I'm just kind of drawing them all together. But do this. These first two lines, the one that's drawn here and the one that's drawn here. If we want to figure out what's going on with the speed, know that the origin over here is at 0. Okay, so that means along our y-axis, that would be a velocity of 0. Anything along the x-axis is going to be a velocity of 0. Let's kind of have our made-up scale. I know it's not scaled totally correct, but there we go. Let's call it 10 to negative 10, and these are velocities in meters per second. These first two graphs are showing us velocity values that are getting closer to the x-axis, closer to the x-axis. Okay, we call that as converging on the x-axis. So when we're getting closer to the x-axis, we're getting closer to a velocity of 0. This is going to be a decrease in our speed. Anytime we see that, that is a decrease in our speed. Now, we have two data sets here, and let's say that we're going to go ahead and just use this for a minute. You going to allow me to grab that one? No. Okay. So what we're going to do is we're going to then talk about what we have in these middle two. Anytime we have a 0 slope, note that as a constant speed. And even if we're to draw this a little bit further away from the x-axis, well, it's just going to be traveling faster because it's further from 0, but that 0 slope is going to tell us that we have a constant speed. Okay, our last two lines we have here, when they're starting to drive away from the x-axis or diverging from the x-axis, okay, we're starting closer to 0 and getting further and further away. From a speed perspective, that is going to be an increase in the object's speed. Okay, so converging on the x-axis, like we see in our first two, getting closer and closer to that, that's going to be a decrease in speed. Any 0 slope, constant speed on this graph. and then anything diverging from the x-axis is going to be an increase in speed. Now we do have, okay, the speed component here, but let's just get to some examples and figure out what we have. Okay, so our first sample, first quadrant graph, straight line, okay, with a positive slope. Remember, the rules we're using are different. So in terms of displacement, all we have to look at on these graphs are the quadrants. Okay, this first graph, we're in the first quadrant, positive displacement. Okay, and in the second graph, we're also in the first quadrant, so that's also a positive displacement. I think it's then easiest to go to acceleration, because acceleration simply is going to be your slope. Okay, first graph, positive slope, positive acceleration. Second graph, negative slope, negative acceleration. Okay, so then what do? We use our converging, diverging to figure out what's going on with our speed. Okay, we're starting in our first graph at a velocity of 0, and we're increasing that value. So that is definitely going to be an increase in our speed. And we did talk about the relationship between displacement, speed, and acceleration in a position versus time graph. Even though the graph is different, we can still use our descriptors to check it. If we have a positive displacement and an increase in our speed, we should have a positive acceleration. Okay, so that is another check for us. Okay, down to the second graph on this page. Okay, we know that we have a negative slope with a negative acceleration. We have a speed that is getting closer to 0. So this is going to be a decrease in speed. Okay, so last two graphs, both fourth quadrant graphs. We know that that means that our displacement has to be negative, displacement has to be negative. We both see that the slope is 0, so the acceleration is 0, and we are going to have two constant speeds. Question is, which one's going to be faster? Well, it's the one that is going to be further from the x-axis. Now, we do make an assumption that those two graphs have the same scales, but we are going to make that assumption as we go throughout the year. Okay, so just a reminder, okay, we go all the way back to position versus time graphs. We have a separate set of rules for position versus time graphs. Use those rules as we go through. Then when we get to velocity versus time graphs, they also have their own set of rules. So make sure that we use them appropriately.